Hello students, today we will be looking at exercise 7.6, the chapter Applications of Differential Calculus, the 12th standard Tamil Nadu board maths. So this exercise mostly deals with absolute and local points, extremum points, that is maxima and minima, and monotonicity of functions, that is increasing and decreasing functions. First we will look at some concepts. So a function is said to be increasing an interval I if a less than b implies f of a less than or equal to f of b for all a comma b element of I. So as we go from left to right, the function keeps on increasing. A function f of x is said to be a decreasing function in an interval I if a less than b implies f of a greater than or equal to f of b for all a comma b in element of I. So this means that as we move from the left to the right side on the x-axis, the function value keeps on coming down. Now, this is a theorem that helps us find the decreasing and increasing nature of the functions. If a function f of x is differentiable in an open interval a comma b, then we say if d by dx of f of x greater than or equal to 0 for all x in a comma b, then f of x is increasing in the interval a comma b. So we look at the first differentiation of the function, and if that is positive, that means it is increasing. If d by dx f of x is greater than 0 for all x in a comma b, then f of x is strictly increasing in the interval a comma b. So this strictly increasing means that the function is not like a constant in during any point in a comma b. It's always increasing. So there's a difference between increasing and strictly increasing. So moving on, if f of x is decreasing in the interval a comma b, if d by dx f of x is less than or equal to 0 for all x in the interval a comma b, and the strictly decreasing, so if the first differentiated value of the function is less than 0, that means it is a decreasing function. F of x is strictly decreasing in interval a comma b if d by dx of f of x is less than 0 for all x in a comma b. So we'll be using these in the problems to find the monotonicity of the functions. Moving on, we will look at some of the interesting points in a function. So a stationary point x naught comma f of x naught of a differentiable function f of x is where f dash of x naught is equal to 0. That is when the function, the first differential value is equal to 0, that's called a stationary point. The second definition is a critical point. A critical point x naught comma f of x naught of a function f is where f dash of x naught is equal to 0 or does not exist. So critical point covers both the stationary point and the point at which differentiation does not exist. Now this has to do with the maxima definition and minima definition. So let x naught be a number in the domain D of a function f of x. Then f of x naught is the absolute maximum value of f of x on D if f of x naught greater than or equal to f of x for all x in D. And f of x naught is the absolute minimum value of f of x in D if f of x naught less than or equal to f of x for all x in D. So we'll look at the complete domain of the function and we find the point where the function is the minimum is the maximum or the minimum. This is the definition of absolute extreme values. So the first derivative test. So this is used to find relative local maxima and local minima. So what? Let's see, local minima and local maxima. They are actually the minimum values in the vicinity. So if a function point is a local minimum, then to the left and right side of it, we have values greater than it. And if a point is a local maxima, to the left and right side of it, we have values lower than it. So the first derivative test is used. So the first derivative test is used to find these values. So let C, f of C be a critical point of function f of x that is continuous on an open interval containing C. F of x is differentiable on interval except possibly at C, then f of C can be classified as follows. And moving across the interval I from left to right. If f dash of x changes from negative to positive at C, then f of x has a local minimum f of C. If f dash if f dash so if f dash of x changes from negative to positive at C, so it's a local minimum. So if you look at this point C3, we see that f dash of x is negative to the left side of it and it is positive to the right side of it. Basically, it is decreasing to the left and increasing to the right. So that defines the local minima. Now, if f dash of x changes from positive to negative at C, that is, then f of x has a local maximum at f of C. So this is shown in point C1, where it is positive to the left side, that is, the function is increasing, and to the right side, it is decreasing. Then we have a local maximum. If f dash of x is positive on both sides of C or negative on both sides of C, then f of C is neither local minimum nor maximum. That is, for example, shown by the point C2, where it is negative to the left side and negative to the right side, so it is neither local minimum nor maximum. So moving on, we will look at exercise 7.6 and some problems in this exercise. So question 1 is find the So in exercise 7.6, find the absolute. Question 1 is find the absolute extrema the following functions on the given closed interval. So we look at subsection 3. F of x equal to 6x to the power 4 by 3 minus 3x to the power of 1 by 3 in minus 1 to 1 closed interval. So to find the stationary point, I'm first taking the first differentiation of f of x, so it's f dash x. So f dash x is equal to 6 into 4 by 3 x to the power of 1 by 3 minus 3 into 1 by 3 x to the power of minus 2 by 3. So on simplifying, we get 8x to the power of 1 by 3 minus x to the power of minus 2 by 3. For the stationary point, we equate this to 0, and I get 8x to the power of 1 by 3 is equal to x to the power of minus 2 by 3. Now rearranging the terms here, so x 1 by 3 divided by x minus 2 by 3 on the LHS, and the RHS I have 1 by 8. So 1 by 3, from the properties of indices, we have 1 by 3 plus 2 by 3 as 1. So x is equal to 1 by 8. And to verify, 1 by 8 lies in the open interval minus 1 to 1. Now we are evaluating the function at the end points of the interval as well. So if we substitute minus 1, so f of minus 1 is equal to into minus 1 4 by 3 minus 3 of minus 1 to the power of 1 by 3. So here first we take the cube root of minus 1, which gives us minus 1, and then we multiply that, raise that to the power of 4, which gives us 1. The second term is minus 1, cube root of minus 1 is minus 1. So we have minus 3 into minus 1. So we get 9 over here. Now we evaluate the function at the right end of the interval, so f of 1. So f of 1 is equal to 6 into 1 to the power of 4 by 3 minus 3 into 1 to the power of 1 by 3. Both these values are 1. So I have 6 minus 3, which gives me 3. Now I'm going to substitute 1 by 8 here. And that is the stationary point to see if it is a minimum or maximum. So f of 1 by 8 is 6 into 1 by 8 to the power 4 by 3 minus 3 into 1 by 8 to the power 1 by 3. So cube root of 1 by 8 is 1 by 2 raised to the power of 4. Cube root of 1 by 8 here is also 1 by 2. So what we have is 6 into 1 to the power of 6 divided by 2 to the power of 4 minus 3 by 2. So what we have here is 3 by 8 minus 3 by 2, which gives on simplification minus 9 by 8. Now we look at all the three values over here and see that the absolute maximum occurs at minus 1, the end of the interval, that is 9. The absolute minimum that occurs at 1 by 8, which is a negative value. So it is minus 9 by 8. So this finishes this problem. Now we move on to the next problem, which is f of x is equal to 2 cos x plus sine 2x, and x is in the interval 0, pi by 2. To find the stationary point, we have to first do the first differentiation, that is f dash of x, equal to 2 differentiation of cos x is minus sin x, so it is minus 2 sin x, and differentiation of sin 2x is cos 2x into 2. Now for the stationary point, we write f prime of x is equal to 0. So what I get is minus 2 sin x plus 2 cos 2x is equal to 0. Now this can be simplified further by quadratic equation. We use the identity for cos 2x, which gives us 1 minus 2 sin square x. That we obtained the expression for the stationary point. Now I'm evaluating the function at the end points of the interval. So the left end point of the interval is 0. So f of 0 I have here is 2 into cos 0 plus sine of 0. So this value is 2 and this is 0. And f of pi by 2 is 2 cos pi by 2 plus sine 2 into pi by 2. So this value is also cos of pi by 2 is 0, sine of pi is 0. So the total value is 0. Now we move on to find the stationary point. To find the stationary point, I write let t equal to sin x. So I have a quadratic expression here, which is 2t square plus t minus 1 is equal to 0. Now solving for this quadratic, I split the middle term as 2t and minus t, because we want the product to be minus 2 and the sum to be 1. So it's possible when we split the middle term this fashion. So I take out 2t common and I have t plus 1 here. Then I take minus 1, t plus 1 here, and I have 2t minus 1 into t plus 1 equal to 0. So writing so the two functions are t equal 1 by 2 and minus 1. So basically sine theta is half and minus 1. Now when we do the inverse, the values of theta which gives us 1 by 2 is pi by 6, and the value of theta, which gives -1, is minus pi by 2. Of these two values, we find that pi by 6 lies in the interval given in the question, whereas minus pi by 2 does not lie in the interval. So we proceed. So only pi by 6 is a valid stationary point. Now to find whether it's a minimum or a maximum value, I find the value of f of x at pi by 6. The value of f of x at pi by 6 is equal to 2 cos pi by 6 plus sine 2 into pi by 6. So this cos of pi by 6 is root 3 by 2, sine of 2 into pi by 6 is pi by 3, sine of pi by 3 is root 3 by 2. So I get the final value as 3 root 3 by 2 here. And we know that 3 root 3 by 2 is greater than 2. It is because if we see root 3 is 1.7 and 1.7 into 3, that gives us a value which is greater than 4. So this value is greater than 2. So the absolute maximum this function has occurs at pi by 6, which is at 3 root 3 by 2. So we evaluated this function at 3 points. If you see here, one is at the left end of the interval, one is at the right end of the interval, the third is at the stationary point. So we find that the maximum occurs at the stationary point and the minimum occurs at pi by 2 and gives us 0. Now we proceed to the next section here, that is find intervals of monotonicity local extremum for the functions. So here I am considering question number 3 and question number 4, subsection 3 and subsection 4. So we have this function as f of x equal to e to the power of x by 1 minus ex. I'm rewriting the numerator as ex minus 1 plus 1, so that the first term ex minus 1 divided by 1 minus ex, that gives us minus 1, and the second term is 1 by 1 minus ex. This will help us to differentiate this easily, because when I do f dash of x, the first term gives 0, the second is we use the chain rule of differentiation, that is we have minus of 1 by this expression square. So it is minus 1 by 1 minus ex the whole square. So it is minus 1 by t square. Then we differentiate what is in the denominator. So d by dx of 1 minus ex. So what I get is minus 1 by 1 minus ex the whole square, and the numerator is minus e to the power of x. So finally what we have is e to the power of x by 1 minus ex the whole square. Now to find the stationary values, what do is equate the f dash x to 0. So when I equate the f dash x to 0, the numerator has to be 0, that is e for x has to be 0. And we know that the exponential function never becomes 0 only at minus infinity. And e for x is always greater than 0 for all or x belonging to minus infinity to plus infinity. Therefore, there is no stationary point. I'm trying to find the critical point. So critical point, as we know, includes the point where f dash of x is 0, and also the points at which f dash of x is not defined. So if I equate the denominator to 0, we have the f dash of x to be infinity or undefined point. So here, when I write the new denominator equal to 0, we get 1 minus e to the power of x equal to 0. for e to the power of x equal to 1. So this occurs at x equal to 0. Therefore, there is a critical point at x equal to 1. So the real x line is divided from minus infinity to plus infinity, and 1 is a critical point in the domain. But we also see that f dash of x is always a positive value because the denominator is always positive and e to the power of x is always positive. So this function is always increasing. So f of x is always increasing function. There is no local maxima or minima. Now the next question is, we are looking at f of x cubed by 3 minus log of x. This is in the interval 0 to infinity. So first, when you do the first differentiation, that is f dash of x, what we get is 3x squared by 3 minus 1 by x. Differentiation of log x is 1 by x. So we get x squared minus 1 by x. Now to find the stationary point, I equate the f dash x to 0. So I have x squared minus 1 by x is equal to 0. Or in other words, while rearranging, I get x cube equal to 1. So this gives the solution as x equal to 1. Now the real axis from minus infinity to plus infinity is divided into two sections, one to the left of 1, the other to the right side of 1. Now to evaluate f dash of x in each of these intervals, so when x lies between 0 to 1, the point which I'm taking the point 1 by 2 to evaluate. So when we take the point 1 by 2, we have f dash of x as 1 by 2 the whole square minus 1 divided by 1 by 2 from this expression. So what I have is 1 by 4 minus 2, which gives minus 7 by 4, which is less than 0. And so the f dash of x in this interval is decreasing. When x is greater than 1, less than infinity, so a point I'm taking is 2. So when I take 2, I have f dash of x equal to 2 square minus 1 by 2, which gives 4 minus 1 by 2, which is 7 by 2. And that is greater than 0. So yeah, so we arrive at the conclusion that f of x is strictly decreasing in 0, 1, and it is strictly increasing in 1 to infinity. And we found that f dash of x is equal to 0 at 1, so f dash of x changes negative to positive at x equal to 1. And to find that value, we have substituting 1, so 1 cube by 3 minus log 1 is 1 by 3. So 1 by 3 is a local minimum. So this function is decreasing to the left of 1, then increasing, that means 1 is the minimum point. I hope so this plotted approximately the function I have plotted over here. This is not required for the final solution. So I hope you understood the concepts related to relative minima, maxima, and monotonicity of functions. If you want the explanation தமிழ்ல வேணும்னா சொல்லுங்க, அதுக்கேற்ற மாதிரி next videos தமிழ்ல explain பண்ணி upload பண்றேன். Thank you.